In this video, we're going to talk about KSP, which is a more precise way to describe how soluble an ionic compound is in water than the solubility rules we used earlier in the year. So when we write a KSP expression, it just represents the concentration of the product ions that would be present, dissolved in the solution. And we don't include, like in the other K expressions, we don't include the reactant because it's in the solid phase. So KSP doesn't have a denominator because it would be a solid. So in this example, we're going to try and define the molar solubility of silver chloride in water. We know that the KSP, which again is the product of the concentration of the component ions, is 2.79 times 10 to the negative 10th. Okay? So if we looked at this process and we made a Rice table for it, initially we have no dissolved ions when we put the solid in. So, none. But we know that's going to go up by some amount, and when we're trying to solve for that some amount, we use the variable x. So the silver ions are going to go up by x, the chloride ions are going to go up also by x, and that's because these have a 1-to-1 stoichiometric ratio, and this would go down by x, but who cares, because it's just a solid. So at equilibrium, we're going to use x to represent the concentration of each of the component ions. Therefore, we can say that x squared is equal to our value for KSP. When we take the square root of both sides of this, we find that x is, which is also the concentration of silver and chloride ions, to be 1.6 times 10 to the negative 5th molar. So we can use the KSP to define the molar concentration of the ions present in a dissolved species. Now, it can get a little bit more complicated if we use something where it's not just a 1-to-1 ratio. And we're going to go the opposite direction here, where we're given the molarity of a dissolved solid, and we're going to calculate the KSP for that. So in this, it's lead iodide, which is going to dissociate into aqueous lead and aqueous iodide ions. Now you can see that it's a 2-to-1 ratio with respect to how many iodide ions you get to the dissolved formula units that you had. So when we write the KSP, like always with K expressions, we have to account for those coefficients using exponents. So the iodide concentration would have a squared value, and lead would just be to the first power. So we can say that the molarity of the lead, again 1-to-1 ratio, is 0.00130 molar, just like was given for the lead iodide concentration that would be dissolved. The iodide concentration is going to be double that because you get 2 of those ions for every 1 lead iodide formula unit that breaks up. When you plug in those concentrations and square the value of the iodide concentration, you get 8.79 times 10 to the negative 9th as your KSP. Now, let's say you were given a system where you have 2 solutions that you're mixing. Let's say we mix 10 mils of silver nitrate that has a concentration of 0.05 molar with 125 mils of 0.01 molar potassium chloride. If we wrote out the reaction, we would see that it would form the precipitate of silver chloride, which has a KSP of 1.8 times 10 to the negative 10th. So, first thing we should do is figure out the concentration of those ions and see how that compares to our KSP when we plug them into our Q expression. So, the volume times the molarity gives me the moles of silver ions. The volume times the molarity gives me the moles of chloride ions. Solving for their concentrations, we simply have to take those number of moles and divide by the volume, which now is 135 mils, or 0.135 liters. When we plug that into our Q, which again is our KSP, but it's just at any point in time, we don't know if we're at equilibrium or not, you have a value of 3.4 times 10 to the negative 5th. If we compare that to our KSP value, we can see that if all of this stuff dissolved, then we would have a way higher concentration of the ions than our KSP would allow. So since Q is greater than K, we're going to end up with the reverse reaction being favored, and you'll have precipitate of silver chloride.